now you've seen how to do profiling with the Scorep, how you can configure Scorep to collect additional information, either by adding instrumentation into the code that's been compiled and instrumented with these instrumentation API. It can also be configured to have less information if necessary. The filtering and appropriate measurement configuration is not only a good thing to do for the profile collection, because then you get better, higher quality, more convenient profiles, something that becomes very essential when it comes to trace collection. And the trace collection is a very powerful technique that gives us additional information about the execution of the parallel applications, but it requires to be done with care. As we saw before, we do a trace collection part, and then there's the ability to do an analysis of the traces. Some of that analysis we'll see tomorrow with Vampire. Some of the analysis we'll do automatically with Scalasca in the course of this session. You already see how you could add various environment variables. You had an environment variable that we didn't look at, which was Scorep enable profiling. That's by default true, so that's why we were getting profiles as the default measurements from Scorep. By turning that off or by turning on the enable tracing, we can actually get trace information. So we'll get a complete history of the execution of every process and thread, a complete set of events that we can then use and see in subsequent measurements. So in principle, it's just a simple matter of enabling tracing to be able to get the traces that we can then analyze later, for example, with Vampire. It's usually not quite as simple as that, because if the traces are too large to fit into memory, then you'll have intermediate flushes that disrupt the measurement during its execution. This typically makes the analysis much more difficult to interpret, if not invalidating it completely. So by doing scoring would tell you how large these buffers should be to avoid intermediate flushes. If the buffers are needing to be made very, very large, that typically means there's just too much redundant information to have a valid and valuable trace. The default here is typically around 60 megabytes. If you increase it to 50 or 100, that's probably reasonable. If you need to increase this total memory for the traces to gigabytes or many gigabytes, typically there's something you should be thinking about doing in a different way. Because this is the amount of memory per process, and if you're talking about hundreds, thousands, many thousands of processes, then the total amount of data that's collected in memory eventually has to be written to disk and then analyzed with the analysis tools. And usually that's not so convenient for very large traces either. Even though we can have efficient ways to write and to read these parallel traces, it just makes life much more convenient and much simpler if the traces are more manageable in size, if the sizes are fit. The analysis that we'll see tomorrow with Vampire, if you're not familiar with it, shows you the execution of each process and thread as a timeline and a nice graphical and interactive display. Before we get there, just this warning to repeat one more time, the traces can very quickly become very large and unwieldy in size. The traces get larger depending on how long the application runs. That's something that you can, by making the execution time shorter, only doing a few iterations instead of many iterations. But that's something that's very much under application control. The other dimension that is somewhat under control is the number of processes and threads. If you're running with 100 or 1,000 processes, that's obviously going to be a larger trace than one from only a few processes. The third dimension where things get large is the amount of data you associate with every event. We saw how you can collect hardware counters, copy counters, and include those with measurements. You can include our usage information for the resource usage. Everything that you add to the trace, all of the events that you don't filter out, is added to the richness, to the complexity, the amount of detail that's in the trace, and that sometimes can be overwhelming. If a trace is not analyzable, storable in memory, that means that we have an option of having to stop measurement at that point, in which case everything after that would be lost. The approach that we currently have is that we stop measurement, we write the data to disk at that point. While that process is writing to disk, the other processes are typically waiting for the next communication, synchronization, barrier point in the application. Once that initial process is finished writing its trace, it can zero its memory buffer and then continue. But then the next process, as it starts executing, probably reaches the point where its buffer is full as well. and then the next one, and then the next one. So you typically end up with a cascade of processes stalling as they fill up their memory buffers and have to write traces to disk. The amount of disk space you require is much larger. If you're not using a parallel file system, everything will be much more inefficient. So that's why you should always be using efficient parallel file systems like Scratch and other systems. It's known as the work file system, but it's typically not the home file system, which is the one you use for building and running your applications. You might think that you can collect a large trace on one platform and then move it somewhere else where you might want to store it and analyze it. Typically that becomes impractical as the traces get larger as well. So often it's the case that you want to do as much of the analysis as possible on the system where the trace is collected. And again, that's something that Scalasca will exploit. Sometimes you need more memory than was available during collection, in which case you might want to undersubscribe the nodes. So instead of fully running a set of processes or threads on a set of compute nodes, if you only run a few processes, maybe they have more memory for the trace analysis available. Scalasca's focus is on automated trace analysis. Rather than allowing you and giving you the power to manually explore and identify all the potential performance problems in large execution trace, Scalasca tries to do a lot of this analysis automatically. So instead of presenting a lot of low-level information, we want to run an analysis on that low-level information, distill it down to something that's much more high-level, much closer to the application level, something that's much more manageable. And in the Scalasca scheme of things, it's presented in this three-dimensional cube format where, again, we have our basic metrics that we can extend, adding additional metrics to. We still have the same set of call paths, execution call paths from the application, and we still have the same set of processes and threads that are being used, but we can enrich the amount of metrics that we determine from the trace data so that you have an enriched, enhanced profile. This project that we started in 2006, it was a successor to a predecessor called Kojak that did all of the trace analysis in a serial fashion. With Scalasca, the focus was very much on making things scalable and being able to handle very large-scale applications. Scalasca 2.1 was released with the Scorep 1.3 version in August, and it included additional support for the K-computer. Fujitsu includes support for p-threads, measurement and analysis. There's a limited amount of p-threads, something that we need to build on and improve. And it also included some analysis where we can identify the critical path of execution and how much time each call path contributes to the critical path. Like Scorep, it's open source with a UBSD license. It supports the same systems as Scorep does and uses the same formats as were used by Scorep. So this is a distinction from its predecessor where Scalasca, the initial version, had its own measurement infrastructure and formats. Now we're using Scorep that's using the OTF2 trace format. We're unable to do an analysis of events and CUDA traces, so it's not so interesting. We're still working out there what sort of CUDA events would be appropriate for this sort of replay analysis. There's some limitations in terms of OpenMP as well. This is the Scalasca workflow, and a lot of it should be already familiar to you. If not, it's presented in this form. You instrument your application with Scorep and you get an instrumented executable. And you can, by configuring that executable through environment variables, you can either get a summary report, which you can then display in a tool like Cube, or you can configure it so that you get event traces collected from each process, and then each of those event traces would be available for analysis with the Scalasca Trace Analyzer. The Trace Analyzer is a parallel application that runs with the same configuration as the measured application itself. That means that if you're running measurement with 100 processes here, you're going to get 100 processes on the same partition of your batch system for the analysis. And distill the trace data that was collected down into an extended and enhanced weight state analysis report where we can present additional metrics that particularly focus on inefficiencies that are things in the parallel execution, the inefficiencies in communication and synchronization. This is an example of one of those. If you imagine we're looking at 4 processes here with time going from left to right, we're seeing 4 processes executing an all reduce. A collective operation, MPI all reduce executed on COM world, involves all of the processes, processes can actually proceed to complete the all reduce until the last one is available to participate. So in principle, the time on processes here before the last one enters the MPI all reduce is waiting time, which in principle could have been used for something else before going into this blocking operation. We call this pattern weighted n by n because it's a collective operation involving all the processes, and any of the processes that join the collective operation before the last one accumulate waiting time. This applies not just to the all reduce, but also the all gather and larger range of functions here, all to all, etc. So all of those MPI operations will involve a set of processes, and some of them will be waiting unless they all happen to enter this all reduce at exactly the same time. For something like a broadcast, we have to differentiate between the root of the broadcast from the other processes. Again, the broadcast is a collective operation. That again means that processes that enter the broadcast early will have to wait, and they can't proceed until at least the broadcast root has participated in the making the information available. Once the broadcast root enters the broadcast operation, then the information is potentially available for those other processes that have reached the broadcast, and the ones which reach it afterwards will get the information available to them. It can be buffered up inside MPI. So again, here the processes before the root process enters the broadcast have waiting time. The root itself has no waiting time, nor does the processes that enter the broadcast afterwards. The same situation happens for scatter operations as well. So this is a late broadcast situation. Or the different processes in the broadcast, we need to know when the broadcast on the root was initiated. That information has to be exchanged between the processes. If we tried to do that exchange during the measurement itself, this would be adding an extra message or an extra operation, certainly extra measurement overhead, which typically is disruptive and we want to avoid. That's why it's more appropriate to store the information locally in the trace and then do the postmortem analysis of these traces. The rest of the time in the communication is to do fewer of them. That's a great thing to do. If you can avoid a broadcast, if you can avoid a message exchange, great, you'll get a performance advantage by not doing it, assuming it was really redundant and not necessary. But if it is necessary and you need to do it, the way to do it efficiently is to make sure that these are non-blocking operations, or if you do need to block, the blocking time is kept as small as possible by making sure that the processes go into the operation at as close as possible to the same time. The way to do that is by eliminating load balances leading into the collective operation. What we've shown for collective operations also applies to point-to-point operations. The simplest case to consider is the point-to-point send and receive using blocking, send, and receive operations, where the receive operation is a blocking operation. It can't proceed until the results of the send are available to it. Here, we're noting the time when the send is started, and the time on the receiver process where it was in to receive early is waiting time. In this case, we'll call it a late sender pattern because the receiver is blocking, waiting for the sender to make the data available to it. You might ask, why do we consider this time here at the beginning of the send rather than when the actual send is initiated itself? Well, we don't know when the send is initiated. That's happening inside the MPI. MPI for us is a black box at the moment. So we can't tell what MPI was doing when it really initiated the send, but we can make a good judgment that it doesn't start the send until it enters the MPI send operation itself. So this is then a conservative estimate of when, how much waiting time on the receiver process was appropriate for the send, for the receive to block, waiting on the send to be initiated. And what happens with blocking send and receive here also happens for the non-blocking case as well. The I receive is non-blocking, but as soon as you go into the wait operation for the result of it, it's going to block waiting on the send here. In this case, we're looking at the receive blocking until the immediate send is initiated, or if both are immediate operations. Again, here there's the blocking time on the wait for the receive until the corresponding send is initiated. By doing a replay of the information in the trace, we can, on the receiver process, know what the receiver is doing, what we do in the replay is that the sender process sends a message to the receiver. The sender process knows who's communicating with, it knows the timestamp of the event that it started. So we just package that up, send it to the receiver receives that information, unpacks it, compares it with its local starting time, and from that can work out how much waiting time it had for that operation. What we're doing is taking the communication and synchronization events as recorded in the trace, we're replaying them with the same configuration of processes and threads, and as part of the replay we can then derive these additional waiting times which tell us which part of the MPI time is waiting time and is therefore something that you should be more focused on minimizing. Of course, you can minimize or try to minimize the time spent in the other MPI operations, but there you're more limited. The only way you can reduce the time in the rest of the MPI send and receive. So let's see an example of using Scalasca in practice with the BT example that we were looking at earlier. We have the Scalasca module already loaded. We're already having an instrumented executable in our bin.scorep directory. So we'll just be using that directory if we're already in that directory on the right-hand side. So we cd into that directory, bin.scorep, so we can reuse that already instrumented executable. Scalasca comes with one command that has 3 phases. The instrumentation part of Scalasca is the instrumentation part, which is now done by Scorep. You don't need to use Scalasca for this directly because you've already used Scorep to do the instrumentation. So it's essentially just backwards compatibility. We provide a Scalasca analyzer nexus. This nexus is a utility that will help us capture the run measurement configuration. It will actually set up some of the measurement configuration for you automatically. But the key thing it will do is set things up in such a way that we can restore that configuration and reuse it for the trace analysis itself. It has a number of different options here for enabling different sorts of analysis, but basically the analyzer comes in the different variants that are needed for analyzing different problems. If it's an MPI application and an MPI trace, then we could analyze that using the MPI version of the analyzer. So there's one version dedicated for MPI analysis. If you're just using OpenMP, there's a corresponding version that just focuses on OpenMP. And if you have a hybrid combination of these, MPI and OpenMP, then we need the dedicated analyzer that can handle both of those options. The third utility that's provided is the Analysis Report Explorer. We shortened the name to Square. Square is something that does some post-processing of the analysis reports, the ones produced by Scalasca, the ones produced by Scorep directly. From these analysis reports, it will derive additional metrics, and then we can see those in the cube display as you were using previously. So Square is a wrapper, a post-processor, preparing additional analyses, additional metrics for presentation in cube. Before we see scan in operation, just to remind you some of the things that it does, it will do a few things as a convenience for you. One of those, it will try and determine an appropriate title for the experiment. You can set a title as you wish. It's completely under your control by setting the experiment directory environment variable, or you can just get a default name as produced by Scan or by Scalasca, based on the name of the executable that you're running, based on the configuration that it's running in, the number of processes, the number of threads, if we can determine that, and the type of measurement that's being done. You can specify things on the command line to the scan command, or you can have things set to environment variables with a precedence order that makes sense. The things on the command line override things that are through the environment variables and override the built-in defaults that are used otherwise. Scan does a number of consistency checks. So one of the things you noticed is that if you do a measurement and you use try and use the same directory name as one that already exists, P moves the original directory to a new location, gives it a different name so that it can create a new one. That's probably not what you want if you're doing multiple measurements at the same time, because the one that's being moved is also active at the point where it's being moved around, and then it typically ends up with corruption. So what scan does is it ensures that the directory that's going to be used is unique and isn't going to corrupt and override one that's you otherwise like to keep. But the key thing that the scan will do, as I said, is to determine the launch configuration and the resources that can be used for doing the trace analysis to do it in as efficient way as possible using the resources that are available for measurement. The job script for the Scalasca analyzer from the job script date directory. So we'll run that and see how it should be the same time as the Scorep measurement. But if we take a look at what it has done, we're using the Scalasca analyze or scan command as a prefix. Here it says MPI exec, but the same thing works with AP run. It's just confirming what sort of measurement it's doing, and it's defining a default experiment name based on the BTMZ executable and based on the configuration of processes and threads, and a summary measurement of the default configuration is being used. So at the start here, we're seeing that the default name that it came up with and the command that it's using to run the application, which was what it was provided with on the command line. We then have the output from the application itself, and at the end, it'll show confirm that everything was collected and stored in this directory. If we do an ls in this directory to see what it contains, we'll see that it contains a lot of the files that we have already seen before. It has the profile, which is the interesting part. It has a copy of the configuration that was used for the Scorep measurement. It saved a copy of the filter file that was specified on the command line. And this scorep.log file is just a capture of the commands and the execution from the output itself. That's already in your batch file output, but sometimes it's appropriate to save it in this directory as well, especially if you're running things interactively. So that's just saved there for convenience. And if we were to run the Scalasca examine command or the square-s command on that, this is going to do the scoring of this profile as we saw before, but it's going to save the profile information in the analysis directory. So because it knows the structure of this analysis directory, it knows what it contains, and it's going to write the score report also into a file in that directory. So it's saving everything in the same place. And if we take a look at the contents, I can quickly look at the score output. It should be the same score output as we got from before with running Scorep manually. So again, it's confirming us the effect of the filtering and the fact that we would need, in this case, 53 megabytes of memory for every process to be able to store that information. So that's convenience to the scoring, which was incorporated in this square command. The next thing I want to show is the square itself, and it will show you the analysis report that it has generated similar to what we had before. But if we go down deep enough, we'll see that there are additional metrics going to show up in the call tree here. So inside synchronization, it's showing the weighted barrier time, the time the processes wait at the barrier before the barrier executes. In this case, it's relatively small. If we look at the communication time, there's very little time in collective communication, so point-to-point is where the time is. And what it's telling us is that more than half of the time in the point-to-point communication is situations where we have this late sender situation. If you right-click on this late sender metric, then hopefully this time we get some additional information about it. So this is just some online help information describing the situation which the metric applies to. So in this case, it's a receive or a wait that is waiting on the corresponding send to be initiated. So we can close that, and if we look at we can see where that occurs and how much of that applies on the different processes. So it's in this wait all. It's only the master processes that are doing the MPI operations. We can see how much of that time applies to each of the processes. It may be that, so this is an indication that there's some imbalance between the different processes going into these exchange operations where they exchange data between themselves. So at least in the trace analysis reports, you can get the additional metric information about these additional metrics. Let's go to this idle threads one that we looked at previously and see what it says in terms of the online help for this. So you can understand what's shown in the picture here. Here we're just looking at what's happening on a single process, and we're considering it executing or having 4 threads allocated and available for it. If all threads are being used, there's no idle time. But when we're executing serial code outside of a parallel region, that means that we have idle time on all of the other cores that were allocated. If we're executing a region where we're not executing that parallel region on all of the threads, if it's limited in some sense to a smaller number of threads, then that means that we'll have idle time accumulated during the parallel region on one or more of the threads. And if we scroll this to the right so we can see the end of the picture, once we exit the parallel region, we're back into serial execution again. We're again accumulating idle time. So here we're taking the notion that you are running in a batch system, you have an allocated partition, you have allocated a number of cores for your execution. You're being charged for those cores whether they're executing or not. And you should be using those cores as efficiently as possible. And that means that your parallel regions should be using as many of the cores that are available, and they should be executing for as long as possible to minimize the limited parallelism associated with not executing on all of the threads, or threads not executing on all of the cores, or where you're outside of parallel regions and you only have serial execution time. This is different from time that is potentially serial execution inside a critical section. In a critical section, there may only be one process executing, but that's going to show up as OpenMP overhead itself. This idle time here is idle time accumulated outside a parallel region. So if you see and where you see that occurring, that's an indication that you're not executing a large enough amount of the code in parallel and not executing it on all of the threads that are available, all of the cores that are available. Let's go further down in the list of metrics. And we were talking about this computational imbalance heuristic before. If we pick up the online help for that, this is a heuristic that we can calculate from information in the profile. So it doesn't come from the trace analysis. It's looking at the execution time of each of a function or a set of functions on all processes. And here they're shown in a histogram. From that, we can work out what the average time is. And if all of the processes took the average time, they would all finish at the same time. There'd be no imbalance, and everything would be well balanced and well optimized. Anytime there's a process that takes longer than average, it's overloaded, it's going to take longer. At some point, other parts of the execution are going to have to wait. And anytime a process finishes earlier, it typically has nothing to do until the next synchronization point. So it will show up as underload on some of those processes. So the time on the processes above the average matches the time on the processes below the average. And in this case, process 6 had exactly the average time. It does not overload, not underload. It would not change. It would not be changed by balancing here. How you do that load balancing, of course, has to be done with additional communication or synchronization unless some additional overheads in some other form. But this is giving you some sort of measure of how much you could potentially gain if you could perfectly optimize, perfectly balance everything, and remove these imbalances on the ranks which are affected by them. If we expand it, we'll see that we have overload and underload time. The processes that are overloaded are matched by other processes which are underloaded. So if we have underload and we select ADI where there's time, so that here the processes that are underloaded are going to be matched by a corresponding amount of overload on the other ranks. So that's a measure of the amount of time that you hope to be able to gain if you could balance things perfectly. But this heuristic is based on the notion that things that are executed in such a way that the balance isn't changing from iteration to iteration. We know that this application does 200 time steps, and it can be the case that the load balance is changing from iteration to iteration. That's going to be lost in the profile because in the profile, all of that information is aggregated together. What we can do with critical path analysis is work out how much time is spent by the processes when they're on the critical path. we're seeing as the 31 seconds in the critical path metric here. And of that 31 seconds, it's saying that there's 3.5 seconds is imbalance, showing up from processes on the critical path. If we select the metric for critical path, it'll explain what the critical path is for those of you who might not be so familiar with it. Again, here we're considering the execution of 3 processes. We all start executing function foo. Foo takes a different amount of time on the different processes. But then at some point there's a communication between process 3 to process 1. They then do some different operations. Another communication ends up with the process bar going into the BAS routine. The critical path is determined by doing a backtrack through the trace by figuring out what's executing at the end, what's taking the longest at the last part of the execution, and then following the communication path through the processes until we get back to the MPI init or the beginning of the execution. Because by following the communication on the critical path, we can identify which functions are on the critical path, and those are the functions that we should focus on and optimizing. In this case, there's a relatively small amount of imbalance in the BAS routine that would help us by reducing the time in BAS. If the time in BAS was made more balanced across the processes, we could save a little bit of time here. You can see also that the time in foo is a bit longer on rank 2. If those were balanced in such a way, these two would take a little bit longer, but this one would finish a bit earlier, and we could immediately remove some amount of time from the critical path. Removing time from bar or from some functions that are not on the critical path isn't going to change the total execution time, because that's just going to result in more time waiting. If we make this bar function here faster, we're just going to spend more time waiting in the following communication before we can continue. If we make foo execute faster here, we just spend more time waiting before this bar call here is, before this communication completes and before this bar can execute. So we need to identify which are the functions and how much time we spend on the critical path, and that's the part of the execution that we can hope to get some performance improvement from by reducing the time there. So again, that's an additional metric that's only available from the critical path analysis and the trace analysis of the critical path analysis of the trace, so the trace has that additional information. We can also see information about the instances. One of the things that I should show you, we select one of these late senders, for example, up here, and showing up. If we do a right click on it, show maximum severity information. So what it's telling us is how frequently that pattern occurred, and it's identifying the most critical instance of that pattern. So it's telling us exactly where in the trace the most severe instance of this pattern occurred. In this case, it's 17.5 seconds into the execution, and it had a duration in this case of 0.02 seconds. Relatively small, but typically there's a lot of these late sender operations, and if you can understand and improve the most severe one, often that can improve the behavior of the others. It's also telling us which rank is affected. So although we can't see the trace at the moment, when we look at the trace with VAMP here, this is identifying which part of the trace we would want to look in to see this particular pattern and to be able to examine exactly the circumstances where it occurred. Do we see any of the other metrics? So maybe the weighted barrier. I would expect to see some level of red dotted highlighting of it, but I'm not seeing it here. So if you select the barrier and right click on it, it should be highlighted. I'm not sure why the highlighting isn't showing up, but we can see the severest instance of this barrier. Again, it's telling us exactly which point in the execution, 30.53 seconds into the execution, the severity of that barrier, and the rank that is the most severely impacted by it. So again, this is information that can help you look at this point directly in the trace with Vampire or with another trace analysis tool to figure out exactly what's going on here. We don't have Cube and Vampire set up that you can launch one from the other here. That's sometimes working in some configurations, but you can manually go to that part of the execution with Vampire and see it and work out what's going on there. I think that's more or less the end of what I wanted to present with Scalasca. We already saw the metric descriptions, the critical path. Did we see the statistics for these metrics? So here, so it's showing the range of severities for that barrier. And if we click on the bar somewhere here, it will also give us information about how often it occurred. So there are 14 instances. Most of them are all very short and insignificant. In this case, in other applications, you may actually show up with more severe values. And if we were able to connect from Cube to Vampire, it would launch Vampire and direct Vampire to zoom in and show just the part of the execution corresponding to that severe instance. But I don't think that's going to work here. You can try it. So it requires Cube and Vampire to be set up so that they can communicate with each other, and that hasn't been set up here. But it would then take Vampire to the point in its execution where it's zoomed in to show the interval corresponding to where that severe instance occurs. And by knowing which ranks are affected, you can also work out how, in this case, it's a, I'm not sure which pattern it is. It's highlighting the weight also. It's some sort of point-to-point operation. I guess it's a late sender. You can figure out which process was affected by that. Here we have process on rank 1, which is waiting for this send to be initiated from rank 3. So that was Scalasca. It's available as an extension to Scorep. It's using Scorep for instrumentation and measurement, providing some additional convenience for measurement collection, additional metrics from the trace analysis or from the processing of the cube files coming from Scorep or from the trace analysis itself. So that's also something that you can try out with the BT example or try it out with your own application codes. As I said, it doesn't have information about the CUDA operations, so it won't be suitable for analyzing CUDA traces, but for MPI and OpenMP threads, it should have the information that's there. That takes us to 20 to 5. You want to start with Vampire, or we just wait for tomorrow, or something else to put in right now? What you can also do is we're hoping that you get as far as being able to look at your traces with Vampire tomorrow. We'll show you Vampire tomorrow and how to use it, but to use Vampire, you still need to have a trace collected. You can look at the trace coming from BT. We already have those collected. We'll look at those with Vampire tomorrow. But if you are wanting a trace from your application, we have to get through the process of instrumenting, producing a profile that we can score, and then determining how large those trace buffers should be, how large the trace should be on disk. It'd be great if you actually contact Felix or I, or perhaps even Joe Marion before collecting a trace, because if it says the trace is going to be 100 gigabytes or 1,000 gigabytes in size, maybe we'll have a better idea to avoid filling the file system, especially if there's more than one of you trying to do this at the same time. So that you can do the scoring and prepare things, and then you're ready to perhaps use setting the environment variable to do the trace collection yourself, or by using the scan command, in which case it will also do the trace analysis for you, and you can look at that with Cube, as you've already seen. Well, the other thing is that we'd actually like you, if possible, to share your experience. And I know that some of you have already had some initial results, and perhaps one or two of you could actually come up here and say a few words about what you needed to do. Some of you needed to do some work to be able to use CMake for instrumentation. Did all of you end up using the wrapper scripts that were mentioned to get a measurement with Scorep? And that was working, at least for some of you. Were there still problems with CMake and CMake Scorep combination? For all of you who are using, you still have some problems that we need to work through? Okay, so that's one of the things that we should definitely try and do today. Once you have got something instrumented, some of you needed to enable pthreads because pthreads was used by your application, and if Scorep isn't able to automatically determine that you're using pthreads, you need to give it a special hint for that. And so that's what at least one guy needed to do before he got a good measurement from his application using MPI for pthreads. Everyone else was able to get at least an initial measurement and to do some scoring and try out some filtering of that initial measurement. So it's an iterative process. It doesn't have to be perfect, but usually there's definitely something to check before we go into the trace collection part. If the trace collection looks reasonable, then we can start doing some traces and prepare those for tomorrow as well. Otherwise, there'll be time to work on those tomorrow. So tomorrow, the plan would be to start at 9. I hope 9 isn't too early for anyone. We started a little bit later today because some of you were traveling from further afield, but the plan tomorrow would be to start at 9 a.m. We'll introduce you to a new example that's going to be including CUDA into the mix, and we'll look at those applications, the existing applications with Vampire, so that you can see what's in the traces, and also look at the additional information that's collected in the CUDA measurements. And we also have a few additional things that we can also talk about, OpenACC support. So there's a lot of things that we can extend into tomorrow, but the key thing is getting some measurements from your applications on the date system. That's what we want to work with you on. Okay, so that's the end of what we plan to present for today. We expand the tree on the right-hand side, we'll see the processes and threads again. As we had before, what's in the center pane is the same as before, so we'll see the iteration we can expand and then see the parallel regions. That's fine for now. What's interesting is that we have a few additional metrics that are showing up in the tree on the left-hand side. Before, you just had a single metric called time. Now we can actually expand time and break it down into different parts, into execution time and idle time. We can expand execution time into MPI time and OpenMP time. And then you can go further and then break those down into synchronization and communication time. So what is done here, if we click on MPI synchronization, that's going to highlight the barriers. MPI barrier, MPI synchronization time. Here there's only one in the application execution, but we can identify the percentage of the total execution time. If we look at communication, that comes in two varieties. There's collective and point-to-point. In this case, there's very little collective communication, but if we select it here, we would see the all reduces. So there's a reduce operation that's used as part of the finalization of the benchmark. So again, here we identify the time for collective execution from the profile. And when you look at the point-to-point time, we'll see the time, in this case, in the boundary exchange, where there's the send, the receive, and the wait all. This is a relatively small example, BTMZ, but in your codes where there's more communication done, it can be more difficult to get an overview of how much time is MPI, how much time it is OpenMP. In this case, we have 2.58 seconds, and we're seeing it that's, in this case, 0.3 seconds of the total execution time. If you were to run this with more processes and fewer threads, the MPI time would grow. It's the collective part of the MPI time that grows most significantly. If we close the MPI part of the tree, we can look at the OpenMP part. Again, we're looking at the OpenMP overheads here. It's showing us that there's a small amount of management time which is used for creating the threads in the parallel region and setting up those threads. So if you select management time, we'll see that that is showing up where expand one of those, and it will show the parallel regions themselves if we go down further to where they exist. So setting up a parallel region is some additional overhead which we can distinguish. Typically, most of the overhead comes from synchronization, which is barrier synchronizations, either explicit synchronizations or implicit. I think there's only implicit synchronizations in this application, and we can distinguish that time. That 72 seconds corresponds to 7.7% of the total execution time. And then when you select one of those implicit barriers, we see the distribution of that implicit barrier synchronization time across the different threads. We can see at a glance that the values on, in this case, thread 2 and 3 are higher values. They're waiting longer. They have spent less time in the computational part, and therefore they have more waiting time at the end of those parallel regions. The critical time is coming from OpenMP critical or OpenMP atomic, or if it was using OpenMP lock API, those would all be distinguished as additional metrics here. There's one more metric that's shown here called idle threads, and that's a little bit more difficult to explain. If we right-click on the idle threads and bring up a description of it, we can learn a little bit more about what that metric is about. Close this. We'll look at it later. What it's going to tell us is it's a heuristic where we try and work out how much of the time is outside of parallel regions and corresponds to where cores are not being used effectively. There's hierarchies also shown here for the amount of data that's sent and received and bytes transferred and collective and point-to-point operations. So again, that can be useful to compare those. At a glance here, we can see the amount of data sent in aggregate matches the amount of data received. That doesn't mean it's the same on every process. It can vary by process, but you would expect all of the data that's sent to be received at some point. There's also a heuristic down here for computational imbalance. That's, again, a heuristic that's looking at the balance of execution time on different processes and threads and trying to work out how much of that corresponds to overload on certain processes and threads, which is matched by less than average amount of time under load on others. We'll see how that metric compares with the critical path metric, which comes from the trace analysis. So essentially what you've seen presented in Cube here has just been a reformatting and rederiving of a few additional metrics and a restructuring of the information that was available in the Scorep profile reports. So you don't need to use Scan for collecting these reports. Scan was provided as a convenience. You don't need to use Square for analyzing these and presenting these, but it's sometimes a convenient way to get an aggregate picture of where different times are spent. And all of that information is coming from local information from the profiles collected by Scorep. What additional information can we get from the trace analysis? That's going to be our next task. So for the trace collection, using the Scalasca analysis nexus is to just add the T flag to it. So if we go back into our job script, scan.sbatch, and modify it, in this case, we'll add a -T flag to the end of this. We still have to make sure that we have the filter file specified, and because we know that we need 53 megabytes of memory, we need to specify that, and rather than specify it on the command line, we use the Scorep environment variable to say that we need 53 megabytes of memory to be reserved on each process for these traces. Then we can just resubmit this. And if everything goes correctly, then we'll have our first traces collected. So the key thing was to add -T here at the end of the Scalasca analyze command. and to make sure that you uncomment the part that is specifying the total memory usage. Some of you had already experimented with collecting traces before, and if you didn't have this value large enough, you'll see that there are additional buffer flush measurement which Scorep warns about. If this environment variable is set too low, that will happen, and the scoring is the best way to determine what is an appropriate value for this. If you add additional information, if you add happy counters, you need to redo the scoring and tell it you're adding hardware counters so that this estimate will be increased. So is that submitted and running, or not submitted yet? The key thing to note here is that without needing to recompile and re-instrument the application, the Scorep instrumented executable had the information we needed that we could reconfigure to collect information for the tracing. If, of course, you need or want to change the information that's in the profile itself in terms of what's instrumented, if you just want MPI information, then you might want to go back and re-instrument it. If you've changed the source code, you'll be re-instrumenting it anyway, so that you have a new executable that's ready for analysis. But if you've changed the code, if you're running it for a longer execution time, it's always a good idea to redo the scoring, because the scoring is dependent on how many processes and threads you're running with. It's depending on your application configuration. Every time you change those, if you're not sure what the impact that's going to have on the buffer sizes, it's always a good idea to do a summary measurement first, score that, and then use the score information to configure the trace buffer size if necessary for the trace collection. Can you see what's in the directory that it produced? I was working on. So it's automatically renamed or given a new name for the new measurement based on the trace extension, because it's a trace measurement. And we'll see a number of additional files in here. The files that actually pertain to the OTF trace data are these files called traces.otf2. That's the file that we're going to be using directly with Vampire. That's also the trace data that's used by the trace analyzer. And inside Scalasca, the trace analyzer is known as Scout. So that's why there's a Scout log file and a Scout.qbex. When we were doing the measurement, the first part was the same. Configure the measurement for the trace collection and analysis. That information gets stored in memory and written to the trace buffers at the end. It's a good idea to take a look into this output file and make sure there's nothing unexpected in there. If it says something about Scorep errors, Scorep buffer flushes, that's usually an indication that something's not configured correctly. But if everything looks clean, if you just have the output that we had from before, the trace measurement overheads, one or two lines above, aren't going to be significantly more than the summarization overheads. So we, again, have only 29 seconds here, which was the same as we had before. So that was the trace collection part. And immediately after the trace collection, it runs and starts the trace analysis. It determined from the configuration that was being used for measurement what it needs to use for the trace analysis. That's saved in the Scout.log file, as well as the output from the trace analyzer itself. So this is the trace analyzer here that's being run. It's being run with the trace data from the trace directory. It's reading the trace data, analyzing it, and then reporting at the end what it did, as well as storing the trace analysis in a new cube file. At the bottom here, it's saying that everything is clean, there's no violations there. It may be that if you're running on multiple nodes, you'll get warnings. If you're on a system where the nodes are not synchronized, the clocks are not synchronized, that means that we don't have a global timestamp that's reliable. That means that we can have events that are apparently received at an earlier time than the sender sent at a different node. What the timestamp correction does, that's applied by Scalasca, is it can apply logical consistency criteria so that it will readjust the timestamps, shift things as necessary so that those inconsistencies and violations are eliminated. That's enabled by default. If we look at the top of the execution command, we actually added the type correct command here on the Cray system because you're typically running with multiple nodes. In this case, it wasn't necessary, but if you're running with more nodes and the timestamps are not synchronized, you'll get warnings, and those are avoidable if you add this flag for timestamp correction. How long did the analysis take? 11 seconds. There's no guarantee that it's going to be faster than your application. The application ran in 30 seconds for the trace collection. Here the analysis took 11 seconds. You should expect some correlation between the two because all of the sends, all of the collective operations, all of the MPI operations that were recorded in your trace are having to be replayed. They're not going to be replayed with the same amount of data. So we're just going to be sending messages, but we're going to be replaying all of those communication patterns. So typically it's a little bit faster. Some of the analysis requires additional operations, the collective operations in particular. Some of them require doing multiple collectives. If things are synchronized, that'll be efficient, but if things are not synchronized at the time those happen, then it might not be so efficient. But as a rule of thumb, you can expect that they're the same order of magnitude for the trace analysis as for the trace collection. So what did we get as a result of this other than this analysis report? That's going to be shown in the scout.cubex file itself. And so I propose that we run, not just cube, just run the square command on it. So you can look at it with cube directly, and then you'll see the metrics that it generated. But by doing the post-processing of those metrics into a more hierarchical form, we'll see how those new metrics fit into the hierarchy that you've seen before and shown in cube. Before we take a look at this, were there any problems with the traces and the trace analysis? Something was found? Or? Yeah. Mm-hmm. You're using the Cray environment? The Intel environment? So the version of Scorep that was installed on this system is installed with Cray MPIC version 7. If you instrumented the application with 6, which is the default version, that means that you're going to have some interesting things in the trace. I can show you those later, but you'll find that it actually sent several terabytes of data between the processes, and this is not actually accurate. So you need to rerun do the Scorep reinstrumentation again, and then you'll have a new executable that you can use for measurement. Was there someone else who had a apparent deadlock in the trace analysis? Yeah. So the trace analysis is relying on the integrity of the trace. If there's things missing in the trace, if it's corrupted in some way, then the replay is likely to deadlock as well. And that will show up either as a deadlock in the trace analysis or at some point in the trace processing. We can take a look at the trace in more detail to figure out what the problems are, but a sure indication that the problem is a deadlock in the trace analysis itself. Everyone else got through the trace analysis okay? Scorep memory initialization assertion. This is from your application. This you were getting before with the profiling, or just with the trace analysis? Yeah, I would expect it to be a general initialization problem. We'll need to come back and look at that with you one-on-one. So let's expand the time hierarchy again. At first instance, it's going to look very simple.